In this video, we'll look at polynomial functions and their graphs. So this will be the first of two videos in which we'll explore this topic. And we'll start by looking at polynomial functions in general. That is, we'll look at polynomial functions of any degree. And then from there, we'll look at graphs of basic polynomials, starting at polynomials of degree 1, 2, 3, 4, kind of working our way up. And then that will be a good jumping off point for starting to talk about the end behavior of polynomials. So I thought for this one we'd start with a definition, and then we'll look at a couple examples just to kind of make sure that we're on the same page with understanding how to talk about polynomials. So for polynomial functions, a polynomial of degree n is a function of the form p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a1 x to the first plus a0, where n is an element of the positive integers and a sub n does not equal 0. Now we need these criteria because if we're saying that this is a polynomial of degree n, if the first coefficient a sub n is 0, then it's not a polynomial of degree n because we don't have a variable with x to the n. And we need to specify that n is in the integers because if it's not, then we're talking about various kinds of roots. So a sub 0, a sub 1, a sub 2, all the way up to a sub n are the coefficients of the polynomial. A sub 0 is the constant coefficient, or the constant term. For a sub n, the coefficient of the term with the highest power, this is called the leading coefficient. And a sub n, x to the n, is the leading term. So first, just want to demystify this a little bit. an minus 1, and a1, a0, all of those coefficients are just numbers, right? They're a half, they could be negative 23, they could be 62, any of those numbers. It's just the number in front of a variable. And we write it like this in general just to indicate that we could have a polynomial that starts with a highest power of 8, it could be 6, it could be 32, but this is just the kind of general form that polynomials take. So let's just look at a quick example to make sure that we understand. So we have p of x equals 3x to the fifth plus 6x to the fourth minus 2x cubed plus x squared plus 7x minus 6. So let's identify the different kinds of things in this polynomial so we can have a common language to discuss polynomials. So the coefficients, and I'm just going to write coef, period. Those are 3, 6, negative 2, 1, 7, and negative 6. The constant term is negative 6. The leading coefficient is 3. The leading term is 3x to the fifth, and the degree is 5. So now you can kind of make those connections. Again, we could have polynomials that look much simpler. We could have a polynomial that just looks like x squared. We have a polynomial that looks like 1 minus x squared plus 3x cubed. We could have a polynomial that just looks like x. So I'll leave it to you to take a moment to identify the different parts of these polynomials here. Now we'll look at graphing some basic polynomial functions. Like I just said, the most basic polynomial function is like p of x equals x. And we know that that looks like just a straight line through the origin with slope of 1, etc. We're pretty familiar with that. So let's graph p of x equals x squared, p of x equal x cubed, p of x equals x to the fourth, p of x equals x to the fifth. P of x squared, that should be one we're pretty familiar with. We know that that'll go through 0, 1, 1, negative 1, 1, and looks like that. X cubed, another one that we've seen before, that goes through 0, 0, 1, 1, negative 1, negative 1, And then once we hit 2, we go way up to 8, and negative 2, we go way down to negative 8. So this I've described before as being kind of looking like a swimmer. Like if you look at their arms, it looks like that. Now to draw x to the fourth, the way I want you to think about this is it's going to take on the same basic form as x squared, but if we're between 0 and 1, if we're multiplying a half by itself 4 times, we're going to be at 1/16. That is to say that the graph of x to the fourth is going to be much closer to the x-axis between negative 1 and 1, and then it's going to grow very quickly once we get outside of that because, for example, negative 2 to the fourth is much bigger and is growing much quicker than 2 squared, kind of at that same x value. It's still going to be at, negative 1, 1, and 1, 1, and 0, 0. But once we're inside and outside of those numbers, it's going to be very small and growing very quickly, respectively. So it'll look like this. So you can kind of see it's a little flatter, a little closer to the x-axis in between negative 1 and 1, and gets much steeper, much quicker outside of negative 1 and 1. X to the fifth, same kind of idea here. We're going to be still hitting those 3 anchor points, negative 1, 0, 0, and 1, 1. But in between, we're going to be much closer to the x-axis, and outside, we're going to be growing much quicker. So it'll look like this. So those are your basic graphs of polynomials. Now with this, it's important to take a look at what's happening at the ends of the graphs, because that'll make it easier it'll make it easier to graph various polynomial functions. So let's start with x squared. If x is getting really big, what's happening to the y value? The y value is also getting really big. We'll typically write that as y goes to infinity as x goes to infinity. As x gets really, really big, traveling way down the positive x-axis, y is going to get really, really big, right? And that kind of makes sense, right? If you're taking a large number and you're squaring it, it's going to be large. And similarly, as we travel along the negative half of the x-axis, y will also get really big there. So we'll say y goes to infinity as x goes to negative infinity. So now we're getting really, really small, but as we get really small, x squared gets really large. So now we're getting really, really negative, and as we get really, really negative, the graph of x squared gets really, really positive and really big. So taking the same kind of approach for x cubed, as x goes to infinity, we would say that y goes to infinity. And as x goes to negative, y goes to negative infinity. And then for the x to the fourth, we got the same kind of end behavior. That is what the graph is doing as we go in the really positive direction and the really negative direction on the x-axis. And same thing with x to the fifth. Now, of course, if we flipped them, if we put a negative in front of either the x cubed or the x squared, then these end behaviors will switch. So for x squared, instead of going to positive infinity as x goes to negative infinity, we would go to negative infinity as x goes to negative infinity. End behavior of polynomials. The end behavior of the polynomial p of x determined by degree n and the sign of the leading coefficient a sub n.